We're continuing our discussion today about tokenization, and we're going to dive into BPE, which stands for byte pair encoding. A lot of people want to know about the BPE algorithm because it's the very first step in creating input for Muppet models. But you don't need to know anything about Muppet models to understand how BPE works. But if you want to understand how Muppet models work, you do need to know how BPE works. So that's why we're starting here. The algorithm was first introduced in the context of data compression by Philip G. Gage, a graduate of the University of Colorado Boulder, but it didn't really get used for natural language processing applications until Rico Sindvik et al. Showed that it was a good way of dealing with rare words in machine translation problems. We'll see why it can help in just a second. The UNC tokens that we talked about in traditional tokenization schemes go away, and this algorithm generalizes without too much difficulty to just about every natural language that you can express with Unicode. Why did this relatively simple algorithm become the de facto standard tokenization for downstream models? The alternative of just using the byte stream of characters as input is not that great. You need a bunch of inputs to understand a sentence, and that ends up being computationally expensive. For many languages, you probably do want to have some level of abstraction so that the elements of meaning are being used as your underlying representation. And for lack of a better term, let's just call them words. Most of the time, we want those words to get their own token. But the nice thing about BPE is that if you don't have a word in your vocabulary, you can still represent it. Let's consider the beautiful German word Rindfleisch-Etikettisierungs-Überwachungs-Aufgabenübertragungsgesetz. For whatever reason, this word is not in the vocabulary, but it still gets represented as a series of tokens, 16 tokens to be exact, and many of those tokens correspond to what we would consider a morpheme. You have auf, which is a preposition in German. You have über twice, which in addition to being an overvalued company is also a preposition. Ungs is a suffix, and while some morphemes get split into multiple tokens, like gesetz, it's not so bad. So you might think that this might have some linguistic motivations because it does find suffixes and prefixes. So for example, in professionalize, you get eyes at the end. In reform, you get re at the beginning and form. In unbelievable, you get un and able as separate tokens. Practically, if you end up spelling a word incorrectly, which happens all the time in real-world data, especially generated by me, it's able to find a solution relatively elegant. That being said, there are probably better ways to do this if you want to have things that are more linguistically plausible. And the relatively simple algorithm ends up with some silly tokenization, such as separating the G in Georgetown, and separating the straw in strawberry. There's a really long story about the bad consequences of tokenizing solid gold Magikarp in this way. If I ever get around to making that video, I'll put the link in the description, hopefully. If you want to play around with tokenization that has been released by AI companies, you can use the Python package ticktoken to load tokenizations and see how it tokenizes arbitrary text. And for many people, that might be enough. But keep watching if you want to learn how to implement this yourself. And I think you should, because a lot of the weird things that these models do are attributable to weird things that happen during tokenization. And if you don't understand how the tokenization got screwed up, you won't understand the weird downstream effects. Okay. Here's the algorithm for BPE. I told you it was simple. To include all bytes as tokens and special characters you want to take care of. Count all the pairs of tokens that you see. Find the most frequent pair of them and replace that with a new token. You keep doing this until you run out of vocabulary or until you don't have any pairs of tokens that repeat. So let's see an example to make this more clear. Let's say that we have the single sentence from Dr. Seuss, The Cat in the Hat. So let's look at all pairs of tokens. The pair TH appears more than any other pair of tokens, so we will create a new token with index 256. 255 of our token indices have been used to account for all of the bytes we could see by themselves. There are 255 of those because a byte has 8 bits. So we repeat the process. The next most frequent pair is token 256 followed by E. That becomes token 257, which corresponds to the word the. We next have token 257 followed by a space. We replace that with token 258. Now that we have fully captured the word the and a space after it, the most frequent pair of tokens left is a T at the end of two words, cat and hat. So we create token 259 for that, and then we don't have any token pairs that appear more than once, so we're done. Now that we've built up our mapping, we can apply it to new text. Let's see an example of doing that for the word that. Of course, this is a very common word in normal English, so it should probably get its own token, but we didn't see it in our training data, so it's not something we have a special purpose token for, so we need to break this down into constituent tokens. Each of the individual characters become its own token, one for T, H, A, and T. We next look, are there token pairs that we can merge? The answer is yes, there are two. Both TH and AT are possible options. We need to choose the one with the lower rank, and that's token 256. We do it in this order because this gives us more opportunities for merges later on that might include this token. But for this example, there aren't any, so the only merge that's now possible is merging A and T into token 259. At this point, there are no further tokens to merge, so this is our output. We don't want to do that for every word, so we want to build a vocabulary up of all of the words that we do have individual tokens for. This will speed up both the encoding and decoding process. The short snippet of Python code you see here builds us up recursively over all of our vocabulary so that we can map tokens directly to strings. Speaking of decoding, let's say that we get a token sequence that looks like this. From the merge data structure, we can directly take the token 257 to the, bypassing the intermediate tokens that were a part of it. We can then move on to the next token in the list, 259, and expand that to AT. Now that becomes a lot simpler. We don't have any previous merge tokens that we need to take care of. So token 101 becomes E and token 104 becomes R. So decoding is just the reverse of this process, going from a sequence of tokens into a string that you could read on your computer. And that's basically it. There are a couple of details you should be aware of if you're actually implementing it. GPT-2 used some find and replace to deal with whitespace, so if you want to have the same outputs, you'll need to replicate that step. There are many cases where you want to warm start the vocabulary. For example, if you know that your documents are in Greek, which uses 2 characters of UTF-8 encoding, you might just want to add those to your vocabulary from the start without forcing the algorithm to find all of the Greek byte pairs. Likewise, you may also want to have special symbols, like an end of generation tag. That means you need to tell the algorithm, don't individually analyze the characters that make up this tag, just treat this as a single token no matter what. Those complexities get repeated in training. You need to use a regex to find those special cases before you begin the merging process. Those details aside, you now know everything you need to know about implementing byte pair encoding. When we talk about other models, you'll see other tokenization strategies. One notable example of this is word piece tokenization. It uses a different objective to find merges, something that looks a lot like mutual information, except it's missing the log. Nevertheless, it's very similar. Turning back to BPE, the subject of this video, hopefully you see why it's so ubiquitous. It's very simple, it's relatively efficient, it works well for English. All that being said, it ain't perfect. It sometimes runs into issues for lower resource languages, low frequency tokens, and misspellings. And oftentimes, when you see a Muppet model doing something crazy, like I said before, the tokenization is to blame. And now that you understand the tokenization and how it happens, you can do a better job of debugging those odd edge cases. Thanks for watching this video. I picked out another video that you can watch up here. If you want to get more context for the videos, check out this link or the link in the description. It gives you readings, programming assignments, and other things that might be more helpful. Finally, help me out and help other people find this content by providing a big gradient to the recommendation algorithm. Like the video, subscribe, or leave a comment down below with mistakes that I've made, newer research that has come out, or just tell me about where you are in your journey.